Hello, Sunil sir. Good afternoon, sir. Sunil Matthew, sir. Our resource person has joined. Sunil
Hello,
sir, can you?
Anjali.
Sir.
Yes, 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 I can hear you.
Sir, very glad to see you, sir.
Yes, thank you, thank you. Same to you.
Welcome to our webinar, sir. Thank you
All
so
right,
much for
thank you.
accepting our invitation.
Okay. Then how many participants are there?
Sir, we are expecting around 80 participants in this Google Meet, but I think some of the participants are from Morocco. So
Okay.
because of the timing change, previous days it was from 10 to 11.
Hmm.
And today it is from 2 to 3, sir. So maybe because of the time change, but we have put it in the group and all. They may be joining soon. We are expecting around 90 to 100 participants in this meeting, and YouTube Live is also there, sir.
All right. So in YouTube, what should be typed actually for seeing the live?
Sir, I'll send you the link, sir.
All right, no problem. I'll see
Okay,
later.
okay, sir. Okay, sir.
Okay. Anyway, it's only 1:50, so I'll be coming in 5 minutes. Is it
Okay,
okay?
okay, sir. Okay, sir. It's up to you,
Fine,
sir.
fine.
Okay,
Thank
sir.
you.
Thank you. Thank you.
Exactly 5 minutes before 2, I'll be here. Okay.
Okay, sir. Thank you so much, sir. Thank you. Sir, so shall we start the session, sir?
Sure. Let us start the session now.
Okay, sir. So I'm Christine. Yeah, so we can start the
Yes,
session.
miss.
Yeah. So good afternoon to all of
Shall
you and
I
over to Anne Christine. Yeah.
start?
Yes. Sure.
Fun all. Today we are going to a webinar series of Pure and Mathematics. First, I'd like to tell you all to close your eyes for a silent prayer. So let's do 1 minute. Yes. So today we have Dr. Sunil Kumar. I invite Jency Miss to explain to talk more about Sunil Kumar, Dr. Sunil Kumar, and to give the welcome address. Jency Miss.
Good afternoon to all. Respected Principal, Dr. Sister Dina Jose, Resource Person of the Day, Dr. Sunil Matthew, DBT Star College Scheme Coordinator, Dr. Sister Sylvie Matthew, our Head of the Department, Srimati K.L. Swarnamis, my colleagues, my dear students, and all other participants. Today is the fourth day of our webinar series on pure and applied mathematics. My hearty welcome to you all for today's session. I am very glad to introduce today's resource person, Dr. Sunil Matthew. Dr. Sunil Matthew is an assistant professor of the Department of Mathematics, National Institute of Technology, Kozhikode. He took his PhD at NIT Calicut in 2009. His areas of expertise are biocomputational modeling, fractal and chaos, and fuzzy graph theory. He got selection by NBHM in 1999 and also got selection by TAFR for research in 2000. He authored many books including Sustainable Development Goals, Analysis by Mathematics of Uncertainty, published by Springer in 2020. I extend a hearty welcome to you, Dr. Sunil Matthew, sir. Once again, I welcome each and every one of you for the session. Now over to you, sir.
Good afternoon, everyone. Am I audible?
Yes, sir, you are audible.
All right, thank you. Anyway, first of all, I would like to thank everyone for inviting me to your prestigious conference.
Thank you, sir.
Okay. So, hope everyone is fine and the conference is going very well. So today, I would like to talk to you something about a new topic. You can even include it as a topic in biocomputational modeling or mathematical oncology or even in basically fuzzy graph theory, wherever you want. So I think I will divide my presentation into two parts. The first part, I will introduce you some basics of fuzzy graph theory. And the second part, we will discuss some of the basic applications of fuzzy graph theory in mathematical oncology, especially in detecting cancers, cancerous tumors by certain clustering techniques. Okay, let me directly go to the presentation now. I share my slide.
Okay, sir.
Okay, hope it is visible. Is it visible?
Yes, sir, it's coming.
Fine,
It's
fine.
yeah.
Thank you.
Yes.
All right. Anyway, see, in 2009, we have studied certain cancer detection problems connected with graph theory and fuzzy graph theory. And one method was presented in 2010 International Congress of Mathematicians at Hyderabad. And the applications mentioned in this presentation was discussed at International Congress in 2010 and was published there. So due to heterogeneity of the audience, I thought first I will introduce you the ingredients for the application or the fundamentals of fuzzy graph theory. And I don't know how many of you have got basic literacy in fuzzy logic and fuzzy graph theory, I don't know. But I assume that nobody among you have got any pre-knowledge in this particular area, so that I am free and I can talk to you in any manner. All right. So I really understand that I have given 1 hour, right? Madam, am I given exactly 1 hour or less than that?
Yeah,
No,
yes,
sir,
sir.
it is
Yeah.
All right. Okay. Anyway, before we go to the fundamentals of fuzzy graphs and fuzzy graph theory, I would like to tell you something about a method which we developed in 2009. Actually, as you know, generally medical people never like a method which is based on pictures. They don't like methods based on graphics. If you take picture and you say something based on that, they don't like it. Let me tell you frankly, but this method was discussed in Cancer Research Institute in Trivandrum, and I have collaborated with 2 doctors there, and we have submitted this one as a project to Department of Science and Technology, Government of India once, and unfortunately it didn't happen due to some problems, not because of the actual mathematical problem, because of some other problems. Anyway, we collected data from cancer institutes, and the segmentation part is their job, imaging part is their job, and the next is, once we have an image, we convert a particular image to a fuzzy graph using certain mathematical programs. As you know, while converting a picture of a cancerous biopsy image, actually we have taken images of glioma, a type of brain cancer, and of course some samples of breast cancer also was used in that particular project. And medical people helped us in taking biopsies, in segmenting images, and finally we were given an image, and we separated background from the cells, and then we transformed such a picture into a graph. That was a big graph. Some computer programs were used. We developed fuzzy graph model. Once we have a fuzzy graph model, we used a fuzzy graph a fuzzy graph based clustering technique to cluster, these cell clusters. And once we cluster, these cell clusters, we use certain graph theoretical parameters, especially distance based, then spectral based, and a few more. We extracted graph theoretical parameters from the converted fuzzy graph theoretical model, and we trained a neural network. And neural network finally predicted inflammation or cancerous cells or even normal cells with 99% accuracy. I had a little experience in collaborating with a mathematical oncology person in Egypt 10-15 years back. And he used ordinary graphs and ordinary graph theoretical techniques to extract clusters of cells in identifying these 3 different types of tissues. Anyway, finally we automated the process, and using the automated software we were able to predict things in a very comfortable way. So that was the overall things we have done in a nutshell. But in order to have a detailed understanding of what we have done, you need to know a little about fuzzy graph theory. And I understand that Sunita madam have discussed something based on fuzzy logic and fuzzy theory in a previous discussion, previous seminar. So I think I can directly go to fuzzy graphs and all. Yeah, again, this is an explanation of the methodology we have adopted. Construction of fuzzy cell graphs from stain biopsy images. Then when we have fuzzy type of things, we have the provision to sort or cluster things in an intelligent way. So an intelligent clustering of FCGs were done. So K-linkage and K-click process were used in the middle. And finally, after that, the tabulation of metric, cluster, and spectral parameters, properties. Okay, once we have these things, we constructed fuzzy neural networks, FNNs, and we trained FNNs with data received from cancer institutes. And we were testing tissues as well. And after training, we tested our tissues and we automated with the software. That's what we have done. Let us directly proceed to, I think it would be better to discuss something about existing graph theoretical techniques to deal with this type of situations. So what you are seeing is simply a bone cancer image. I think you will make an eyes, you can distinguish between the background and cells, but generally it is not possible, as you know. This is called Voronoi diagram. Voronoi diagram is a mathematical technique where we, cluster cells and predict the behavior or nature of that particular biopsy image. But it is not an accurate one. And why we have targeted or why we have attempted in such a method is this. We just looked into the existing methods like Voronoi diagram and we found that it is not at all accurate. And then the Voronoi triangulation, that again is simply related with the graph theory. Graph theory techniques are used here. As you see, they are using triangle graphs inside. But unfortunately, it's again not an accurate thing. If you provide 100 samples, only 75% times, it will give you an accurate data. So that also is a failure. I could say a failure. Now, simple cell graph. That is again a method discussed in 90s and in the beginning of 2000s. As you see, they have clustered things in a better way. As you see, these blue portions represent clusters of cancerous cells. And of course, they are connected. They might have extracted distance-based properties, then click-based properties. You are seeing certain clicks here and there. So many things. But unfortunately, that method also was not successful. That is only 81.1% successful. Okay. So we studied all these three different methods and concluded that none of them is providing a very, very, very believable score. That is why one more is their ECM aware cell graph. That is an extension of the previous simple cell graph method. And a little good actually, it gives 90% accuracy, but still far away from the expected target, as you can see. All right, if somebody is interested, I shall provide you some of the references for these different varieties of methods which are used in identifying cells as cancerous, inflammatory, or normal. Fine. Anyway, this only literature survey. This I will give you more details about this in the last slide. Of course, we are going to fuzzy graph theory now. Little bit only, not too much. So even though it started in 1975, fuzzy logic was introduced in 1965 by an Iranian American mathematician called Zadeh, Lotfi Zadeh, and he passed away. Actually, I was about to meet him in Calcutta, and he died in previous year. You know that. So he only introduced fuzzy logic. Due to fuzzy logic, we have plenty of applications around us. We are using fuzzy logic based washing machines, fuzzy logic based submarine trains, underground trains, fuzzy logic based traffic systems. A number of applications are developed based on fuzzy logic. All right, by the development of fuzzy graph theory thereafter, we could do further. I'll tell you more applications of fuzzy graph theory after some time. This is a very simple example. In the field of computer science, we have a very famous problem called bottleneck problem. The bottleneck problem, you face bottleneck every day. You're all having internet with your mobile or with your computer. Sometimes, you may get less number of packets. You may experience some sort of lagness or some sort of delay in that particular internet connection. Remember, it is not getting disconnected. It is just getting delayed. Sometimes you may have to wait for 5 minutes to send a message in your WhatsApp. Sometimes it will go very quickly and you will hear tick tick sound in a fraction of seconds. Why it happens? It happens because of the delay in the network. Why delay is happening? I'll just give you a very simple example. Suppose you have a bridge. Suppose there are 3 roads coming to one side of the bridge and another 3 roads coming from the other side of the bridge. What will happen? What will happen is a very simple thing. So all the bus, trams, trucks and bikes and motorbikes, they all will come to the bridge together and they have to wait for their turn for some time. So that will cause some sort of delay. You may have to apply a little bit of queuing theory in order to sort out the situation there. So that is a very difficult situation. And even that bridge may collapse in time because of our law. There is a very famous physical, brain related problem. You are aware of that. You have several problems, like what I say, forgetting things. So memory loss, many brain related issues are there. They may be due to vulnerable links and vulnerable nodes. You know that there are thousands of neurons in your brain connected by axons and synapses and axons. If traffic always passes through one particular route, suppose you always think about some tragedy. In 6 months' time, you will be addicted to the tragedy and it may be very difficult for you to get rid of that. Because that traffic is, will affect you after some time. Some neurons also will get addicted. Sometimes you may get, there are possibilities of physical problems of such a thinking process. Don't worry about such things for the time being. So these are all examples of networks. Why we need fuzzy graphics? Generally, when I study internet connectivity in Britain and in India, you know that the speed is very much different. You know that South Korea is having very high speed, whereas China is having moderate speed. India is okay, sufficient speed. But there are countries without much speed. So comparison altogether is a very difficult task. So you may have to do it in a very normalized way. So the normalization is possible only with this type of graphs, fuzzy graphs. Fuzzy graph theory will help you in normalizing man-made as well as these natural networks. So that is a very basic set for the requirement of such a graph. All right, let us very quickly visit Sardai's theory and Rosenfeld's theory in 5 minutes. All right, Sardai's fuzzy set theory is something like this. You might have heard about Sardai's set yesterday. It is simply a mapping from a set into the closed interval 0, 1. What is the advantage of such a mapping? Suppose S consists of all girls in our country and your mapping is 0, 1 into 0, 1. My mapping, I would like to call it as beauty. All right, beauty. So girl number 1, depending on my sense of beauty, I can assign 0 or 1 or some value in between. If I say 1, she is completely 100% beautiful. And if it is 0, to me, she is not beautiful. It's a relative concept. If I'm assigning 0.5, all right, it's okay. It can go to the left as well as to the right. That's the meaning. So if you're considering the collection of cards of red colors, if it is completely red, I can assign the value 1. If it is black, I can assign the value 0. If it is somewhere in the middle, of course, I can give something in the middle. So the thing is, when we assign fuzzy value to an element, some sort of intelligence is coming. See, in Japan, underground trains are running without any drivers. Why? There is a camera focusing the train line all the time. The camera will absorb the pictures. The picture will go into the computer. Computer will process the image and the image will give to the fuzzy controller. Fuzzy controller will decide whether to stop or run. Fuzzy controller based on the available experience. If it is a piece of, a trunk of a tree, a small piece of a tree, it will give membership value of 0, otherwise 1, and the train will go as it is. But if the picture is recognized as a human being, it will never, run. It will stop exactly in time. So if it is 0.5, it will have some sort of, dilemma, and it will reduce the speed. If it is something off life, it may escape in that time. So that is what is the advantage of Sardai's logic. That fuzzy logic helped to change the world actually to some sense. All right, now comes why Sade, after Sade, Rosenfeld introduced fuzzy graph theory? The question and answers are like this. You know, a graph is a way of representing information involving relationships between objects. And objects are represented by nodes of the networks and relationship by arcs. And when there is a vagueness in the description of the objects, or in the relationship or in both, it is natural we think about a fuzzy graph model. Let me give you a simple example. Suppose we are constructing a railway network between 2 or 5 different locations of the country. Suppose one route is it's a hilly, the contour is very, very zigzag and very difficult to construct a rail line between those 2 destinations. We cannot predict the exact amount to be utilized in the very beginning. But we can compare. We can say other directions are comparatively better than this. So this may need more money comparing others. So that comparison will induce something like a fuzzy logic and a fuzzy graph, a fuzzy membership value, and we can construct a fuzzy graph model which may be accurate in some sense, not always in an exact sense. Remember. So this is the definition of fuzzy graph given by Rosenfeld in 1975. A fuzzy graph is a non-empty set V together with a pair of functions. Let me tell you one thing now. Fuzzy graph theory is a beautiful subject. Unfortunately, due to the we are not giving any propaganda or publicity to this subject. There are only a few pockets around the world. One is in USA, one is in Iran, 1 or 2, 3 in India, 2 in Pakistan, and as far as my knowledge is true, 1 in Egypt and in few countries alone. So if there are participants hearing me from other countries of the globe, I would like to tell you, you may start doing some research in fuzzy graphs and fuzzy logic. And we have written 3 books for you in 18, 19, and 20. Myself and one professor from United States have written 3 books. You may be, I'm asking you to read those books and start research very next day itself. There are plenty of scope for research in this area. It's only in the beginning. It's only in the very basic infant stage. So there are plenty of scope for research in this area. I invite everybody attending this conference for doing some sort of research in this area. See, what you are seeing in the picture is simply a illustration of this definition. Suppose you have 2 tanks. Suppose you have a pipe connected between the tanks. How much water can be flown in either directions? I'm assigning no directions, so it can be from X to Y or Y to Z. It is clear that the minimum amount of these 2 tanks, that's the maximum possible. Am I right? Yes. So that minimum. So the flow through the edge XY can be maximum, minimum. That is what is this. That is what is this. The flow mu xy is always less than or equal to minimum of the container tanks or capacity of the tanks. If you have an internet network, instead of tanks, you may have routers. The router capacity is very, very important. Maximum line capacity will not exceed the minimum of the router capacity. So that is, and of course, since we normalize things, maximum value we can assign is 1. So there are fuzzy sets assigned both to vertex set as well as edge set. And the edge values should not exceed the minimum of the end vertices. Okay, this is what is the definition of fuzzy graph. Hope you understood the things. All right, consider a fuzzy graph of this type. Now, in this picture, just look at V1 and V4. Between V1 and V4, what is the maximum flow possible? Suppose they do represent something like routers. What is the maximum bandwidth? Computer science people, internet people will call it bandwidth. Transportation people will say widest path. And from discipline to discipline, its term varies. So you can see that the width of this path, V1, V2, V4 is the minimum of this 0.3 and 0.5, that is 0.3. Whereas the width of this path is the minimum of 0.2 and 0.6 is again 0.2. And width of this path is 0.2. So the maximum possible width is 0.3, or in other words, the maximum bandwidth from V1 to V4 is 0.3. So that is referred or called as the strength of connectedness between V1 and V4. Fine. Similarly, you can calculate the strength of connectedness between any two pair of the vertices of this particular graph. This concept is highly applicable in transportation networks, in neural networks, in computer networks, in elementary neural networks, everywhere this connectivity is important. It gives the maximum flow possible through two destinations. Okay, and such a path is called a strongest path, or a widest path, or a maximum bandwidth path. There are several terminologies related with that. Okay, so that maximum bandwidth path is an important concept in this development. Yeah, I will finish this basics in 10 minutes, don't worry. As I told you, in these networks, there are vulnerable edges and vulnerable links. If the entire transport is moving through one network, one particular bridge, one particular arc, in future, there's a chance of that particular bridge may collapse. Similarly, if everything is going through one particular node, that pair may get damaged, that particular node may get damaged in future. Such nodes are called vulnerable nodes. Such bridges, the edges are called vulnerable edges or bridges. In fuzzy graph, we call them fuzzy bridge and fuzzy cut node. Okay, fuzzy. So what will happen in fuzzy case is, see, in graph theory, if you remove one edge, if the graph becomes disconnected, we call the edge as a bridge. If you remove a vertex and the graph becomes disconnected, we call it as a cut vertex. But in this case, we are not worried about disconnection. We are just worried about strength of reduction of flow between some pair of vertices. As the size of the graph increases, it becomes a horrible problem. Finding the strength of connectedness between pairs and determining whether a particular point is a partially cut vertex or a partially cut node or a partial bridge. It is really a difficult problem. We have done some progress in this particular area, but not completely. Identification of cut nodes and bridges in a fuzzy graph. Okay, this is an interesting thing. See, there are loops in internet, there are loops in neural networks, there are loops in brain networks, but that loops may be having some vulnerable edges. So, if you remove that particular vulnerable edge, you may get the ordinary tree structure. A fuzzy tree is defined as a structure where you can identify certain elementary vulnerable edges whose removal makes a connected graph which has no cycles. That is what is a tree. Okay, so you must go through this definition. A fuzzy graph is said to be a fuzzy tree if there is a unique maximum spanning tree in the graph. Now, there are certain other definitions. An arc is said to be strong if its weight is at least as great as the connectedness of its end vertices when it is deleted. And an XY path is called a strong path if P contains only strong arcs. And if X and Y, if XY is a strong arc, we say that X and Y are strong neighbors. So in this picture, you can see that this red arc is strong because its weight is 0.6, while the strength of connectedness from V4 to V3, excluding these edges, is only 0.2. So the weight of the edge is greater than the strength of connectedness between these pairs in this edge deleted graph. Okay, it is heavily raining outside here. I hope I am audible to you. Okay. Now,
Yes,
this
sir,
concept
yes,
is important. This concept is important in the application. See, in that conversion of, from the biopsy image to the fuzzy graph, they made complete fuzzy graphs. There are certain ideas behind it. A complete fuzzy graph is one where every pair of nodes are connected by an edge with a minimum value, minimum of the end vertices. So V4 and V2, 0.7 and 0.5 are the values. we assign the minimum 0.5. So everybody is connected and their values do simply is the minimum of the end vertices, minimum of the end vertices. Such a graph is called a complete fuzzy graph. Now, this division was made in 2009 by us. An edge or arc in a fuzzy graph is called an alpha strong edge if its mu xy, its strength is greater than connectedness of its end nodes. And if they are equal, we call it as a beta strong arc. And if it is less than, then we call it as a delta arc. And there is an additional type of arc called delta star arc if it is not the weakest arc of G. Okay, this is an example. Alpha, beta, and delta are explained in this. Up, you can do it yourself with this presentation. There are several theorems. I will skip many of them. I will just tell you a few and we'll go to our problem. Okay. Now, this is a theorem, and this theorem characterizes bridges in a fuzzy graph. This theorem says an edge is a fuzzy bridge or it's a vulnerable bridge, vulnerable edge, if and only if it is alpha strong edge. And an edge is a strong arc if and only if it is an arc of a corresponding maximum spanning tree. I told you in case of fuzzy tree, there is exactly one maximum spanning tree. Okay, another corollary, in an F tree, an arc is alpha strong if and only if it is a fuzzy bridge of G. Okay? And this one characterizes fuzzy trees. In a fuzzy graph G, a fuzzy graph is a fuzzy tree if and only if it has no beta strong arc. Now, of course, if the path contains only alpha strong edges, it is called an alpha strong path. And if it contains beta strong edges, it is a beta strong path. And this is a theorem which characterizes fuzzy trees. It says a graph is a fuzzy tree if and only if there is a unique alpha strong path between any two nodes of G. And this particular theorem is about the maximum spanning tree of a fuzzy tree. You consider a spanning tree of a fuzzy graph, and that tree becomes a maximum spanning tree if and only if it contains no elementary delta arcs. Further, an MST is unique for G if and only if G contains no beta strong arc. I'm skipping certain theorems because many among you may not be interested in theorems. Okay, these theorems compute the number of alpha strong edges in complete fuzzy graphs, etc. So I'm simply skipping them. If somebody is interested, let them please read this, go through this PPT, and then it will see. Now, anyway, let me tell you one more thing actually. Those who have interested in fuzzy graph theory, as I told you, characterization of fuzzy bridges and fuzzy cut nodes was a big task in the beginning. You know that a fuzzy graph without fuzzy cut nodes is called a fuzzy block. So identifying a graph to be a fuzzy block was a really challenging problem. And many have tried and few have succeeded. But even today it is not complete. There is plenty of scope in continuing research in this identification of blocks in fuzzy graphs. I have given some reference at the end of this. If somebody is interested, they can go through that and they can start doing research in this particular area. Now, let me go to the problem. What you are seeing now is a stained biopsy image. What you are seeing in the picture is a cancerous cell, a cancerous tissue. Okay, it is stained biopsy. You can see this one is again a stained biopsy image of a normal tissue, and this one is simply an inflammation. Stained biopsy image but inflammation. Okay, I think a doctor can distinguish these three quickly at a glance, even with naked eyes. Okay. Now, what we have done is in the process of identifying whether a tissue is cancerous, inflammatory, or normal, the first step is this. First step is to make fuzzy cell graphs. You start with original tissue image and obtain the gray level values in 0, 1. See the gray levels, you can see it is in 0 and 1 here. Okay. So you have the biopsy image, you obtain the gray level values in 0, 1. In the second step, obtain a fuzzy cell graph. You apply a grid on the image with an appropriate grid size. Okay. All right, that grid process is available in the paper. If somebody is interested in the process, I will give you the paper. Okay. Once you have a grid, you will represent each grid as a node. And each grid is a fuzzy set. For example, if grid 1 consists of 4 pixels with gray levels 0.1, 0.3, 0.5, and 1, the fuzzy set sigma equal to this, okay, that represents that grid. And let us represent the entire graph as G. Fuzzy cell graph is termed as G. Then sigma of grid 1, that is the average gray level of that particular block. So remember, in each of these there are several pixels are there. The average pixel value or gray level value will be taken as the sigma value of that particular grid. And in that way, once you have the nodes, you have to construct complete fuzzy graphs. And for complete fuzzy graph, you just need information about the vertex strength, because the minimum of the vertex strength will be taken as the edge strength. Vertex strengths are available because of the gray level values, the average gray level values. So you can construct a complete fuzzy graph in this manner. Okay. Remember, this cannot be done in an ordinary computer with ordinary paint or something of that sort. You need some algorithms, then only you can generate this type of cell graphs. And once you have cell graphs, in one of the 2009 paper, I have introduced a clustering techniques called a k-mean clustering in fuzzy graphs. Okay. So the concept of fuzzy node cut and fuzzy arc cuts were used in that particular method. The concept of fuzzy node cuts and fuzzy arc cuts were used in that particular method. Due to time constraint, I am skipping these slides. So from the fuzzy graph, you can extract two things. One is the fuzzy vertex connectivity and second one is fuzzy edge connectivity. Extract those things. Right, I am skipping that particular portion. Now, once you have these two values, you can think about construction of threshold graphs. A fuzzy graph is T fuzzy edge connected. If it is connected and its K dash T connectivity is greater or equal to T for some T. And if K dash T equal to T dot, then G is T fuzzy connected for any T less than or equal to T dot. There are some very important results in this particular procedure. And T fuzzy edge component, that is a maximal T fuzzy edge connected fuzzy subgraph of G. Using these components are important in our construction. Now, using such components, we will construct a matrix called the cohesiveness matrix of G. And it is defined in this manner, M equal to Mij, where Mij is the cohesiveness of the edge Vi Vj. And the cohesiveness of the vertex Vi is I equal to J. So the procedure is, T fuzzy edge connectivity procedure is, obtain the cohesiveness matrix M of the fuzzy graph, then obtain a threshold graph GT, and the maximal complete subgraphs of GT are the T fuzzy edge component. So we are looking for T fuzzy edge components. Okay. Anyway, in the previous example, see, consider this fuzzy graph. This is a fuzzy graph, even though there are no graph pictures. This one is a matrix. This matrix can generate a fuzzy graph. This can generate a fuzzy graph in no time. Okay, right? And once you have this fuzzy graph, you can obtain a cohesiveness matrix in this fashion. Cohesiveness matrix was explained before. A cohesiveness matrix can be constructed. Once you have cohesiveness matrix, you can get threshold matrices in this manner. Then you can calculate G.5, G.3, G.4, etc. Then these, depending on the levels, you will be getting different clusters of these. Okay, so you can cluster such a fuzzy graph model using an intelligent technique. Using an intelligent fuzzy logic technique, you can cluster things in a nice way. And see, these clusters indicate that T equal to 0.5, for example, indicates that DEHI is a cell cluster. It's a cancerous, whereas its neighboring areas contain the cells B, C, and G can be found inflammatory. Okay, and certain things are healthy. Anyway, the final conclusion is not based on this clustering. Extract the clustering parameters. Once you have clusters, identify distance properties of the graph between these clusters. You can use simple metrics in this particular process. And there are several other parameters also. For example, number of nodes, number of cells in the tissue, number of edges, number of hypothesized interactions. There are several parameters. Extract those parameters from the cell graphs. So these are all certain examples. Eccentricity of a node, closeness of a node, diameter maximum eccentricity, radius minimum eccentricity, number of central points, hop load value for hop edge, hop load exponent, etc., etc. Okay, and still there are graph properties: connectedness and clickness, clustering coefficient, joint connected component ratio, percentage of isolated points, percentage of endpoints, trace sum of the eigenvalues, and energy of certain eigenvalues. Okay, this much can be easily identified. Once we have these parameters, we have identified 12 parameters, form a fuzzy neural network. We formed a fuzzy neural network of this type, and we trained the neural work using the data obtained from the Cancer Institute, and then we checked the data from the Cancer Institute, and with 99% accuracy, we formulated a procedure in identifying cells as inflammatory, cancerous, and normal. And that is what we have done. This can be found in 2010 proceedings of International Congress of Mathematicians held in Hyderabad. Okay, if somebody is interested, I can send you the paper to you. Anyway, that's what I have to tell you. Now it is question time. If you have any questions, please ask your questions. These are the references used. So the Italian person I have told you is Gunduz, J. Gunduz, and B. Yenner. They are from Egypt. And for those who are interested in fuzzy graph theory, you may refer these three. These three are my books published in 2008 and 2009. Okay, at least few among you will pursue research in fuzzy graph theory. Thank you. And it is question time. It is heavily and very heavily raining outside. Even I cannot talk to you. That's the problem. I'm sitting in my office, but heavy thunderstorms and rain is coming outside. So, any questions?
Thank you, sir. Sir, I
Hello.
wanted to ask.
Yeah.
Hello, sir. Sir, can you hear me, sir?
I cannot hear you because of the rain.
Sir, can you hear me now, sir?
Yeah, I can adjust. Okay, no problem. Come on.
Okay, sir. So I'll speak a bit aloud.
Okay.
Sir, my question is, you told that it should be a complete fuzzy graph.
Yeah.
So why is it necessary that it should be complete? Can we model it using any other fuzzy graph, sir?
Yeah, you can do it. But why we preferred for complete is that's the easiest one. Once we have
Okay,
the
okay.
idea about the end vertices, it can be done. Otherwise, your job is double. You have to model it once again. We don't know what exactly is the value possible for each and every edge. So you can do it. It is possible.
Okay, sir. Okay, sir.
Anyway, I request some of the participants to do that particular job.
Okay, sir.
Try some
Okay.
alternative methods.
Okay, sir.
Okay.
Sir, one more doubt, sir. For
Yeah.
cancer study only, we can use this one or any other biological paper.
Pardon?
For only cancer study, is this type of modeling applied or any other
No. For cancer detection, there are plenty of models in mathematics. You can model it using differential equations. You can use statistical methods. You can use it certain there are plenty of methods. Even ordinary graph theoretical methods are available.
Okay, sir. My question is for any other modeling also we can use a similar technique, right?
Sure, you can use similar techniques for modeling other things.
Okay, okay, sir. Okay, sir. Thank you. Now I request the participants to please do ask doubts a bit louder so that he can hear you. Thank you. Sir, also some of the participants would like you to share the PPT, sir. Will that be available, sir?
Yeah, I will share my PPT to you.
Okay, sir. Okay, sir. Thank you. Thank you, sir.
All right. If there are no questions, I will stop here.
I request the participants to please come forward with the questions fast so that we can wind up the class immediately. Participants, if you have any questions, please do ask immediately, please. Yeah, it's only comments are coming, sir. Comments are coming in the
I
chat
can see
box.
the
Yeah.
comments. Thank you very much.
Okay, sir. Then
Anyway.
then over to Megha for vote of thanks.
Okay, thank
Sir,
you.
sir, one question, sir. Sir, one question by Gaurav Mishra. Hello, sir.
Hello.
Sir, one question is asked by Gaurav Mishra. Is it necessary that graphs have to be connected?
Not necessary. I will give you the paper also. Don't worry about it. I can share my paper as well as PPT to you. You can go through it and you can interact with me whenever and wherever needed. Okay?
Okay, sir. Then over to Megha PM for vote of thanks.
Thank you.
Thank
Good
you, sir.
afternoon, everyone. It's my great privilege to propose a vote of thanks to our distinguished guest, Dr. Sunil Matthew. I must mention our deep sense of appreciation for Sir's explanation of the topic, Introduction to Fuzzy Graph and Application in Cancer Detection and Study, the most relevant one for today. It gave deep insight into the topic, and I'm sure that it enhanced all of our understanding pertaining to this topic. On behalf of Nirmala College Mathematics Department, I express my sincere gratitude to Sir for his valuable talk. Thank you, Sir. Finally, I would like to thank Anjali Miss, Sarna Miss, Dolly Miss, and Miss for making this webinar a great success. And once again, I thank all participants in the webinar. Thank you all.
Thank you, Megha. Thank you.
Thank you. So please do wait while the feedback form is being inserted in the chat box, please. The link will be put in the chat box soon. I request all the participants to please wait for the feedback form. Yes, the participants, please do fill up the feedback form. It is given in the chat box. And thank you once again for your participation. Thank you all. The next session will be on 11th December. Please note, all of you, 11th December, 2 to 3 p.m. The link will be shared to you through the WhatsApp. Thank you all. Thank you.
Kelly ma'am,
Yes, sir.
Swarna ma'am,
Yes, sir. Yes,
ma'am,
sir.
the feedback form is not accepting the permission.
Okay, sir. Let us see.
You,
Let
you,
us see.
you should.
Please wait, sir.
Yes,
We'll
madam.
see.
Please wait, sir.
Okay,
Please
madam.
wait,
Thank you.
sir. Wait. Yeah. Okay. Okay. Thank you. Thank you. Yes. Now, can you please check, sir, whether it is working?
Yes, madam. It's opening now.
Yeah. Okay. Thank you, sir. Thank you, Jack, sir, for that. Thank you.
Thank you, madam.
Yeah. Thank you. Thank you.
Thank you, ma'am.
Yeah. Thank you so much. Thank you. And sorry for the trouble. Okay. It was some technical issue that was there. Sorry.
I mean, it's happened. Don't worry.
Thank you. Thank you. Thank you. Thank you,
This is
sir.
not our problem. No, it's a technical issue only.
Yeah. Thank you, sir. Thank you so much. Thank you.
Thank you, madam.